In this lesson, we're going to be looking at solving some equations that have radicals in them. We're also going to be looking at some square roots and negatives a little bit later on. But we're going to start off talking about solving equations that have radicals in them. So let's start off with a really simple example that we don't really need to do a whole lot for. We can really get kind of with common sense. And that's square root of x equals 3. And so in other words, we're saying the square root of something is 3. The square root of what is 3? Well, even without really doing a whole lot, we can say the answer is 9. I know that x equals 9 would be a solution here. I don't know if there's other solutions maybe too, but x equals 9 definitely is. But in order to come up with a process here, we then want to say, what did I just do to both sides? So let me actually write this in a little bit better math just to make sure that we're clear. Then when I say what is x and I say x equals 9, how did I get that from the original equation? Well, I wanted to undo the square root. And so what might make sense then is to say I can undo a square root by squaring both sides. So that would be a reasonable way to get x equals 9, is to square both sides. And so then that begs the question, am I allowed to do that? Is that legal in math? Are we allowed to square both sides? Well, it seems like maybe sure. But then if I actually ask you, hey, tell me the specific rule that you're allowed to do that with. Well, we've got the addition property of equality that says you're allowed to add the same thing to both sides. We have the multiplication property of equality that says you're allowed to multiply the same thing to both sides. But we don't actually have a rule that says you're allowed to do whatever you want to both sides. There is no such rule. Now, we're going to see a little bit later on this course that you can do the same thing to both sides as long as you can undo it. That's really what the rule is going to end up being. But then we got to say, well, can you undo squaring? Well, to get to the answer here of is this legal? The answer is actually kinda. There's not really a rule that says we're allowed to do it. It's kinda legal. So what do I mean by kinda legal? What I mean by kinda legal is by squaring both sides, we will actually get all the correct answers to our radical equation. But the problem is we might get some other answers as well. And let me show you why. The problem is when we square both sides, we could take something that was false, square both sides, and end up with something that's true. So what that tells me is I could actually have originally had something where when I plug the x in, it doesn't work. And yet after doing the squaring and solving and stuff, it seems like it would work. That's a problem. So just to exemplify this, what if I started off with the equation negative 3 equals 3, which isn't really an equation because it's not true, it's false. But what if I took this not true equation and squared both sides? Well, negative 3 squared is 9, and 3 squared is 9. I end up with something that's true. So in terms of solving an algebraic equation, if I did that with square root of x equals negative 3, and I squared both sides, I would get x equals 9. Well, if I actually plugged this back in and said, is it true that the square root of 9 equals negative 3? No, that's not true. So what does that mean for us? What does that mean for solving equations? What that means is if you square both sides, you must check your answer. So this is really the second time in this course you have to check your answer. The first time was when you had x's in the bottom because that could have made a division by zero problem. Now we're going to say squaring both sides isn't quite legal. So if we square both sides, we have to check every answer we get back in the original. And that's really important to check it back in the original. And this is not just checking to see if we made a mistake. You could do the problem 100% correct and get what we call an extraneous solution. By extraneous, the first 5 letters of extraneous there are extra. It's an extra solution. It's one that doesn't actually work. So an extraneous solution is one that doesn't work and we need to throw it away. and see what answers we have left. So let's go ahead and look at solving this example. So in order to solve this, we do have the radical by itself on one side, and so we're going to go ahead and undo that radical by squaring both sides. But as we were just saying, squaring both sides isn't quite legal. So as soon as you square both sides, you should make a note to yourself that you need to check any answers that you get. And we're going to do that off to the side. And I'm going to write it in red so that I don't forget. Now back to our problem. Squaring that left side should be really easy. We're squaring a square root, and so we just get the stuff underneath. We're just left with 2x minus 3. Now the right side should also be easy. This is just a simple multiplication fact. 9 squared is 81. And now from here, we can add 3 to both sides, divide by 2. And this is what I call the potential solution. We're not going to circle this answer yet because we have to check it. So we need to go back into the original and check this answer and say, is the square root of 2 times 42 minus 3 really going to equal 9? So is the square root of 84 minus 3 really 9? Is the square root of 81 really 9? Yes, it is. Now here's where you want to be a little bit careful, where I see little errors happen. I see an error happen where I see people write 9 as their answer. And of course that's incorrect. We got to go back and say x equals 42 is the solution, the answer. The 9 over there was where we were checking our answer to make sure that the left side really did equal the right. Now because it checks out, x equals 42 really is the answer. Now this next example, we want to step it up in difficulty just a little bit. We don't want to square both sides right now because if we squared both sides right now, we see that we have two terms over here and we end up getting a middle term, and that middle term would still have a radical in it. And so that's not a good thing. So whenever possible, we want to get the radical by itself, and that when we square both sides, the radical goes away. So let's go ahead and subtract the 2 to the other side. Now we'll square both sides. Now we're again going to make our note to ourselves that because we squared both sides, we better check any answers that we get. Now the left-hand side, we're squaring a square root. So we get 4 minus x, we just get the stuff underneath. But the right-hand side, we're squaring a binomial. So you either need to FOIL this out or use your formula for a squared plus 2ab plus b squared. Now what you have is a quadratic equation. You have an x squared equation. To solve a quadratic equation, we get everything to one side so that the other side is 0, and then we factor. So we're going to add an x to the other side, and we're going to subtract 4 from both sides, making both 4's go away, and leaving just 0 there on the left. So now to factor this, we're going to factor out the greatest common factor of x, and then set each factor equal to 0, giving me x equals 0 or x minus 3 equals 0. And this gives me my two potential solutions of 0 and 3. We need to check both of these solutions back in the original though. So let's go ahead and test x equals 0 first. And that's going to give me the square root of 4 minus 0 plus 2 is supposed to equal 0. Square root of 4 plus 2 is supposed to equal 0. 2 plus 2 equals 0. 2 plus 2 does not equal 0. So that means x does not equal 0. That's not one of my solutions. I need to throw that out. But let's test x equals 3 and see if it works. So when we test x equals 3 back in the original, we got the square root of 4 minus 3. We're going to add 2 to that. and we're going to see if we get 3. So that's the square root of 1 plus 2 is supposed to equal 3, or 1 plus 2 equals 3. That looks to be true. And so x equals 3 is the only answer that we report here. We're not going to say x equals 3 and no solution or anything weird like that. We just have one answer. The other one just didn't work. So we threw it out. Let's look at a cube root example. When we were dealing with square roots, we undid the square root by squaring both sides, and so it should be reasonable to say that if I have a cube root, I probably want to cube both sides. And sure enough, that's exactly what we're going to do. When I cube both sides, I end up with just x plus 1 on the left, and negative 2 cubed gets me negative 8. Now I subtract 1 to the other side, and I get negative 9. Now you'll notice in this one that I didn't write down that I need to check my answers, and that was actually on purpose. You only need to check your answers when you square both sides, because that's where we're going to introduce a problem. Cubing both sides isn't a problem because of the fact that when we cube a negative, we still get a negative, and we're not losing information. So we'll get into the details of why that's okay a little bit later on in the semester, but for now, just realize that it's perfectly fine to cube both sides. And of course, if you want to check your answer, it's always a good idea to check your answer. It's just not a necessity here. So now we're going to get into the hardest type of radical equations, and that's when we have two radicals in the same problem. So basically what's going to happen here is because we've got these two terms with radicals, that once we square both sides and we end up with a middle term, we're still going to have another radical left in the problem. Which means we get that thing by itself and square both sides again. We're basically going to have to square both sides twice. Now, while it's not a mathematical necessity, I do have a suggestion for you, and that's what you want to write down here in your notes, is that whenever there are two square roots in an equation, like this problem here, you should try to get them to opposite sides of the equal sign. And again, this is not a mathematical necessity. It's just going to make your life an awful lot easier. Because if you try to square both sides right now, the middle term that you get, the 2ab term, would be disgusting because you have these two radicals forming the 2ab. But by separating the radicals, your 2ab term is going to be a little more reasonable. So let's look at what's going to happen with that. Let's go ahead and subtract the root 2x to the other side. Now that we have them separated, now we can square both sides. And because we're squaring both sides, we need to make that note to ourselves that we better check any answers that we get. The left side is the easy side to square in this case, because we're just squaring a square root, so you just get the stuff underneath. But on the right-hand side, this is where we have two terms. So because we have two terms, we're going to do the a squared, so we're going to square the first term. Then we're going to do the 2ab. So remember that when we're multiplying radicals, that 2 is outside the radical. So I'm going to write it up here, for the 2ab, we have 2 times 3 times negative root 2x. Outside the radical, I have 2, 3, and negative. That makes negative 6 root 2x. And now for my b squared, I'm squaring the root 2x, so I just get 2x. So now I still have a radical in the problem. I don't want to square both sides yet because the radical's not by itself. So I want to start moving stuff around until I have the square root by itself. So the first thing I would do is subtract 2x from both sides, which is kind of nice because those x's completely go away. I get 5 equals 9 minus 6 root 2x. I'm then going to subtract the 9, getting me negative 4 equals negative 6 root 2x. Now I could go ahead and divide both sides by -6 before I square both sides, but that's going to introduce a fraction in my problem. I don't know if I want to do that. Now I do notice that both sides are even, so maybe in this case what I'm going to do is divide by -2. That's going to leave me with 2 equals 3 root 2x. Now we're going to square both sides again. We don't need to right check your answers again because we're already going to check whatever answers we get. 2 squared is 4. And now we want to be careful about how we square that right side. We need to square the 3, which gets us 9. We also need to square the square root of 2x, which gets us 2x. So we're looking at 18x on the right. If we divide both sides by 18, we get x equals 4/18 or 2/9. We still need to check this answer of 2/9, so we're going to come all the way back to the beginning and check x equals 2/9. So 2 times 2/9 plus 5 inside the radical plus the square root of 2 times 2/9 is supposed to equal 3. So we have the square root of 4/9 plus 5, and instead of 5 I'm writing 45/9 because I know I need a common denominator, plus the square root of 4/9 is supposed to equal 3. So I'm going to get the square root of 49/9 plus the square root of 4/9 is supposed to be 3. So that's 7/3 plus 2/3, which would be 9/3, which is in fact 3. What that tells me is that x equals 2/9 is in fact the correct answer. Now, in some of our problems, we will be dealing with the Pythagorean theorem, so I just want to take a moment to remind you that the Pythagorean theorem is a two-way street that says a squared plus b squared equals c squared if and only if a, b, and c form a right triangle. And so what we mean by if and only if is we mean if you have a triangle such that a squared plus b squared equals c squared, then it has to be a right triangle. It has to have a 90-degree angle in it. But it goes the other way too to say if it's a 90-degree angle, if it does have, if it is a right triangle, then it's true that a squared plus b squared equals c squared. And it's important as we're looking at the Pythagorean theorem here to realize that the c, the square that's by himself on the one side, is across from the 90-degree angle. It's called the hypotenuse. The a and the b are called legs. So when we're given an example where you draw the picture and it results in a right triangle, we're going to use Pythagorean theorem to solve for the missing side. So in this problem, we're told a cable is to be attached to support a telephone pole, and because of surrounding buildings, sidewalks, and roadways, the cable must be anchored exactly 15 feet from the base of the pole. Telephone company workers use 28 feet of cable to connect the pole and the stake on the ground. How high from the base of the pole can the wire be attached? So we need to draw this picture and see what's going on. So in this picture, we have a pole. I'm going to label it as such. We also have the ground. I'm going to label it as such. Let me erase that little mark that I made down there. Now, we also have the wire. So this is the picture of what's going on. Now, as we start to fill in these values, it's important that we fill them in the right place. Now, we're told the cable must be anchored 15 feet from the base of the pole. Now, the base of the pole is right there. So I know that my 15 feet is either there or there. Now there are a couple of keywords to tell me which of those is the correct one. One keyword is anchored. The fact that it's anchored is typically into the ground. Other keywords are that because of surrounding buildings, sidewalks, and roadways, which those are all things in the ground, the other thing that helps me out is I know where my variable should be. My variable is asking for the height. So I know my variable should be the height, and I know that the 15 should be my distance over here. And I'm told that 28 feet is the amount of cable or wire that I have. So if I go ahead and pull these numbers out, just so that it's a little bit less messy of a picture, I've got H, 15, 28. Once I have a triangle drawn from the information given, I can use the Pythagorean theorem, which says leg squared plus leg squared equals hypotenuse squared. We can subtract the 15 squared to the other side, and then take the square root in order to solve for h. At which point we can go ahead and use our calculator. So we can take the square root of 28 squared minus 15 squared and get an answer of about 23.6 feet. And like with any word problem, we want to say, hey, does this make sense? And so if we look back to our picture and say about 23 or 24 feet up, well, that makes sense, because if we were any higher than 28 feet, our cable or our wire wouldn't even reach the ground. So we know that we're less than 28 feet off the ground. Now, we also know that if this was too short, it wouldn't even be tight. So a 23.6 foot high tie off here does seem to make sense. We're going to change gears a little bit now. So earlier on in this unit, we talked about looking at things like square root of -9 and saying that's not a real number. And we just left it at that. We didn't say what it was. We just said it's not a real number. But I told you at that point that there actually is an answer, and there is something that exists that is just not real. And so now we're going to look at how is it that we can take the square root of -9 and get an answer. We're going to start looking at what we call imaginary numbers as well as complex numbers, and that's going to help us to define negative square roots. Now, the first thing that we need then is to talk about the imaginary unit, which is I. So to take a step back for a second, when you hear unit in our normal real number world is 1. 1 is our unit. It's what represents a single piece, a single number. So when it comes to imaginary units, I is how we define an imaginary unit. It's defined as the square root of -1. But that means then that if I were to square both sides, I squared would be -1. This is how we define the imaginary unit. Now, imaginary numbers are different from real numbers. So one of the things that we've got to be really careful of is to say, there's a lot of times in math that we've learned rules, and in those rules, in a textbook, they'd show up as a shaded box. And that shaded box often had these words in there. For all real numbers x, blah, 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 blah. So there's a lot of times that rules were given to us that only worked for real numbers. So we're going to talk about that as we start to move forward, that there's a couple cases that we got to be a little bit careful of, that if we're dealing with imaginary numbers, some of the rules that we've used in the past don't actually apply. So we're going to have to be a little bit careful. But let's go ahead and look at some very basic examples on using imaginary numbers to begin with. What's going to help when we're looking at these examples is to basically go through our process of simplifying radicals. Break it up, take the radical, clean it up. And in the break it up step, if there's a negative underneath the radical, we're going to break off the square root -1 as its own thing. So if I want to take the square root of -16, I'm going to break it up as the square root of 16 and the square root of -1. Where the square root of 16 I know is 4, and the square root of -1 I know is I. And please note that it's important that this is a lowercase I. Capital I does not mean the same thing. That's not your imaginary unit. So this is 4I. Now, similarly, when talking about the square root of -3i, I could break this up and say square root of 3 is the positive part. It's not a perfect square. But then I can break off the square root of -1. The square root of 3 copies down, but then the square root of -1 is just I. And so we're doing the same idea of break it up, take the radical, clean it up. We're just saying, hey, one of the radicals I know how to take is the square root of -1. So I can apply the same thing to this third piece in the example. The negative that's sitting out front just copies down. But if I'm going to break up -18, I can break it up as the perfect square of 9. What's left of 2, and then the -1. That would get me -18. Now if I take the radical, the negative copies down. Square root of 9 is 3. Square root of 2 copies down. And square root of -1 is I. So we're looking at -3 root 2 I. So earlier I was talking about the rules of certain rules in math that don't work for imaginary numbers, that only work for real numbers. One of those rules is our product property for radicals. So when we're looking at the square root of -3 times the square root of -5, I can't simply call this square root -3 -5. That doesn't work because that rule of multiplying radicals, that product rule, only worked for real numbers. So before I can try to use these, I have to turn them into imaginary numbers first. So that's kind of interesting. So let's go ahead and actually do a couple examples along those lines. If I want to combine square root -3 times square root -5, I need to first of all call this square root 3 square root -1, square root 5 square root -1, which makes this square root 3 times I, and square root of 5 times I. Now I times I would get me I squared. And now that I'm looking at square root 3 times square root 5, those really can multiply together now because they're fully real numbers. Those would get me square root of 15. But then remember that I squared is -1. So this actually gets me negative square root 15. And I can apply similar reasoning with this other problem here, where I'm looking at square root of -36 would be the square root of 36 times the square root of -1. Well, square root of 36 is 6. Square root of -1 is I. Square root of -1 is I, giving me 6I squared, or 6 times -1, or -6. So when simplifying, we got to remember that I squared is -1. Otherwise, I just sort of gets treated like a variable. And we're going to see that as we move through the rest of this lesson, that we can basically treat I like a variable with the one exception that if you get I squared, you'd know that's -1. So up to this point, we've been dealing with imaginary numbers. Let's throw a new definition out there. And the new definition is a complex number. A complex number is a number that can be written in the form a plus bi, where a and b are both real numbers. And so in other words, what's going on here is that we have a real part. So that's our a is the real part because a doesn't have an I in it. There's nothing imaginary going on there. But then bi, that's my imaginary part because it does have an I. So a complex number is a combination of real with imaginary. And as I was just saying a moment ago, when you're adding or subtracting, multiplying, dividing, anything you're doing with complex numbers, you're just going to treat I like a variable. The only thing that's different is if you get I squared, you replace it with -1. So we're really just going to combine like terms in order to add and subtract with complex numbers. So here's a couple examples of adding and subtracting with complex numbers. Now in this first example, I want you to notice that your parentheses are completely redundant because it's addition. This isn't multiplication. This isn't foiling going on. So we could really write this without. Now instead of plus negative, we could just think about this like -3 plus 2i, and that's just combining like terms. We've got our real terms, the 2 and the -3. Those add up to -1. And then we've got the imaginary terms, the 3i and the 2i. That adds up to 5i. And that's it. Now I do want to point out that the order you write this in does matter. We do write in a plus bi form where the real part comes first and the imaginary part comes second. Now I'm not going to get into the specifics of why that's the case, but I am going to be picky about it, that we do want to make sure we do this in the right order of a plus bi. And it basically has to do with the fact that if we were to plot complex numbers, we plot them actually in like a two-dimensional world where you're, instead of an x-axis, you have a real axis. Instead of a y-axis, you have an imaginary axis. So you'd almost be plotting these like an ordered pair of a comma b. That's why the order actually does matter. Now back to the subtraction example. As you'd probably guess, all you're going to do in this example is distribute the negative. If you distribute the negative, it becomes +1 and +3i, and then you can combine like terms. We have -4 and 1 gets us -3. We've got -2i and +3i gets us I. And that's it. Now I will tell you, these are so easy that it's easy to just sort of escape your memory as far as studying. Make sure to pay attention to whether you're just adding and subtracting, which is the easy case, versus multiplying. So look for that symbol in between your parentheses and say, hey, is this one of the easy cases of just addition and subtraction? If it is, I'm just combining like terms. So as we start to move forward to talk about multiplication with complex numbers, again, I is just going to be treated like a variable with the added rule that if we see an I squared anywhere in our problem, we replace that with -1. Otherwise, we're going to just follow our normal rules of multiplication. We're going to do FOILing, distributing, whatever the case might be, and just anytime you get an I squared, replace it with -1. So let's take a look at these examples. For the first example, we're just multiplying four things together. -4, I, 2, and I. -4 times 2 is -8. I times I is I squared. Now we did just say anytime you see an I squared, replace it with -1. -8 times -1 is 8. And that's all we're looking for an answer on that one. For the second part of the example, we're just going to distribute. We're going to distribute 2i to each of those, giving us 8i plus 6i squared. But now instead of I squared, we replace it with -1. So this is 8i minus 6. But remember that we want to write this in a plus bi form, so we want the real number first. The real number is -6. The imaginary is plus the 8i. So that's how we'd actually write this answer as -6 plus 8i. Let's move forward to this example. If I want to multiply the complex number 2 minus 5i by the complex number 1 plus 3i, hopefully it looks obvious that we're going to want to FOIL. And that's exactly what we're going to do. We're going to do FOIL, where the F is the first times the first, and we get 2. The O, or the outside, is 2 times 3i. So that gets us plus 6i. The I, or the inside or inner, is negative 5i times 1 to get negative 5i. And then our L, our last, is negative 5i times 3i to get negative 15i squared. Now, my suggestion to you is not to combine like terms at this step, even though you could. My suggestion to you would be to say, let's replace the I squared with the negative 1 first. So we have 2 plus 6i minus 5i, and then negative 15 times negative 1 gets us positive 15. And this way we can then do all of our combining like terms in this step. I don't like to do combining like terms and something else in the same step. That's when your brain starts to get confused and you make errors. So now we can go ahead and combine like terms. That 15 plus 2 gets us 17, and 6i minus 5i gets us positive I. And this is a plus bi form with the real part followed by the imaginary part. All right, let's look at some of our special formula multiplications. So in this first example, we have a perfect square. This is where we normally do a squared plus 2ab plus b squared, so that we square the 3. We take twice the product. So 2 times 3 is 6. 6 times negative I is negative 6i. And then I squared is I squared. But then anytime we see an I squared, we replace it with a negative 1. And then we combine like terms. And it really is as simple as that. In the second part of the example, this is a difference of squares. We have a squared minus b squared is what we should be seeing. 4 squared is 16 minus 9i squared. But negative 9 times negative 1 becomes positive 9. 16 plus 9 is 25. And one thing that's really interesting that should jump out at you about this example is that I multiplied together two non-real complex numbers. So I multiplied two numbers together that had i's in them, and the answer didn't have an I. So when you're multiplying complex conjugates together, you're going to end up with a fully real number, because with the a squared minus b squared, everything becomes squared, and all your i's go away then. That's really nifty, and that's going to be important for the next thing we want to look at. So in our last example, we saw that when we were multiplying conjugates together, we got a fully real number. The i's were gone, which is awesome for us to know, because that means that if we're multiplying conjugates together, we can get i's out of the picture. So we do call a plus bi and a minus bi complex conjugates of each other, but they're really the same idea as the complex of the conjugates we've been using anyhow. So what we want to move into now is we're going to talk about doing division of complex numbers with like 2 plus I over 1 minus I. But we don't want to really do division. What our actual goal is basically to rewrite this as a plus bi. In other words, we want to get the I out of the bottom. So if you want to think about this as getting the I out of the bottom, we're going to treat this just like rationalizing denominators. When we were rationalizing denominators, we were trying to get the radical out of the bottom. So that's really the same thing. Our approach is going to be similar. We're going to say that when there are two terms in the bottom, we can multiply by the complex conjugate, and that'll make everything into a perfect square and make the i's go away. But if the bottom only has one term, then all we have to do is multiply by I, and that'll bring us up to an I squared, which will also make it go away. So that's the idea, is very similar to rationalizing denominators. When we were rationalizing denominators, if there was a single radical in the bottom and no addition or subtraction, we just multiplied by a radical in the top and bottom. But when there was two terms, we multiplied by the conjugate. And so the same thing's going to go when it comes to these complex numbers. So let's do an example of each. The first example has only one term in the bottom. So all we need to do is multiply by I in the top and bottom. And again, this is 1, so it's perfectly legal. That gets us 7i in the top, 3i squared in the bottom. But I squared is just negative 1. And then instead of a negative in the bottom, we put the negative out front. Simple as that. Now, if we have two terms, we're going to multiply by the complex conjugate. The complex conjugate of 2 minus 5i would be 2 plus 5i. And so we're going to multiply by 2 plus 5i in the top and the bottom. Now, in the top, we're going to have to FOIL that out. We're going to have first, outside, inside, last. And in the bottom, we have a difference of squares. So we're going to square the 2 minus square the 5i. Now, my suggestion to you at this point is don't worry about combining like terms or anything else. Just handle the I squareds. So in this step, as soon as you see I squareds, that's the only thing you want to deal with, the only thing that you want to handle. So instead of 15i squared, we have 15 times negative 1, or negative 15. In the bottom, we have negative 25 times negative I squared. So that becomes plus 25. Now we can combine like terms. And so up top, I have 8 minus 15 is negative 7. And I have 20i plus 6i is 26i. And in the bottom, I have 29. Now, this is not an acceptable way to write my final answer, because I want to write my answer in a plus bi form. So I want to distribute the 29 to each of these, writing it as negative 7 over 29 plus 26 over 29i. So there's my a plus bi form. And this is important, that we do want to write it in this way as a true complex number rather than as a complex number in the top divided by some real number. All right, the last thing we're going to talk about is going to be powers of I. So we've already talked about the first two powers of I to the first is just I. And we've said that I squared is negative 1. So let's talk about I cubed and then I to the fourth and keep going from there. So starting off with I cubed. I cubed, you could think about as being I squared times I to the first. Hopefully that's clear. But then I squared is negative 1. And so really I cubed is negative I. How about I to the fourth? I to the fourth you could think about as being I squared times I squared. Well, that would be negative 1 times negative 1, which is positive 1. Make sure you know those first four powers of I. This is really important, and I'll explain why, that we know these first four powers of I. Because let's look at what I to the fifth would be. Well, I to the fifth would be I to the fourth times I to the first. But I to the fourth is just 1. So really, I to the fifth is just I. And how about I to the sixth? That's I to the fourth times I squared. I to the fourth is just 1, so it's just I squared, which is negative 1. And how about I to the seventh? Well, that would be I to the fourth times I cubed. I to the fourth is just 1. I to the eighth would be I to the fourth times I to the fourth, which is just 1 times 1. And so we can see that a pattern gets formed. If we know the first 4 powers of I, being I, -1, -I, and 1, then they just keep repeating. Because of the fact that I to the fifth is just I to the fourth times I to the first, and we keep on going and going. And so really what we can see is that if you take your power of I and you divide by 4, we don't care about what the quotient of that is, what the answer to the division by 4 is, but if we look at the remainder of I, that tells you which row you're on. And in other words, it tells you what your power of I is. So if you divide by 4 and just look at the remainder, that's your power of I. So let's do some examples of that. So if I want to know what I to the 17th is, then I'm just going to take 17 and divide by 4. Now, it'll go in 4 times with a remainder of 1. Now again, I don't care that it goes in 4 times. I care that it's remainder 1. Because what that tells me is that it's the same thing as I to the first, which is just I. Let's look at why that's the case. I to the 17th would be I to the fourth raised to the fourth times I to the first, because that's 16 plus 1. But if I to the fourth is just 1, 1 time to any power is just 1. I don't care what's going on over there. All I care about is the remainder, how much is left. So how about I to the 20th? How many times does 4 go into 20? It goes in 5 times, but most importantly, what's the remainder? It's nothing. So the remainder of 0 says this is the same thing as I to the 0, and anything to the 0 power is 1. Why is that the case? Because I to the 20th would be I to the fourth raised to the fifth, with nothing else after it. And that's just 1 to the fifth, or just 1. We could go as high as I to the 42nd. We can go higher than that for that matter. But the process stays the same. We say, how many times does 4 go into it? Well, it goes in 10 times, and the remainder is 2. With a remainder of 2, that tells me I'm equivalent to I squared. I squared is equivalent to -1. And again, the reason this works, I to the 42nd would be the same thing as I to the fourth raised to the 10th times I squared. That'd give me 40 plus 2. I to the fourth is 1. 1 to the 10th is 1. So all that I'm left with is the I squared, which is -1. So what if I want to simplify I to a negative exponent? Now, my suggestion to you, and there's a couple different approaches you can take to this, but my suggestion to you is to rewrite it as a positive exponent first. And you can do this by multiplying by I to some multiple of 4. So what I mean by that is you can multiply by I to the fourth, you could multiply by I to the 8th, you could multiply by I to the 12th, you could multiply by I to the 16th, you could multiply by any of those values until your negative exponent becomes positive. And why is it okay to multiply by any of those values? Because I to the fourth is 1. I to the 8th is 1. I to the 12th is 1. I to the 16th is 1. And multiplying by 1 is always acceptable. So if I want to look at the example of I to the -9th power, and I want to try to rewrite this to simplify it, I could multiply by either I to the fourth, I to the 8th, I to the 12th, I to the 16th. So remember that when you have I to a power times I to a power, just like x to a power times x to a power, you add the powers. 4 plus negative 9 isn't going to get me positive. 8 plus negative 9 isn't going to get me positive. But 12 plus negative 9 would. So what I'm going to choose to do is multiply by I to the 12th power. In doing so, that results in I cubed. And I cubed, as we know, is just negative I. And that's as simple as we can make it. It's just say multiply by I to some multiple of 4, so I to the 4th, 8th, 12th, 16th, until you're dealing with a positive power. Once you're dealing with a positive power, then you handle it like normal.